For the past couple lectures, we've been talking about Roth's theorem, and we saw a proof of Roth's theorem using Fourier analytic methods. And we saw basically the same proof, but in two different settings. Right, so 2 lectures ago, we saw a proof in f3 to the m, and basically the same strategy, but with a bit more work, we were able to show Roth's theorem with roughly comparable bounds over the integers. Today, I want to show you a very different kind of proof of Roth's theorem in the finite field setting. So first, let me remind you, the bound that we saw last time for Roth's theorem in f3 to the m gave an upper bound on the maximum number of elements in the 3AP free set that were of the form 3 to the n over n. And so this proof wasn't too bad, right? So we did it in 1 lecture. And then with a lot more work, and people tried very, very hard to improve this, and there was a paper that got it to just a little bit more. And this was a lot of work. And this was something that people thought was very exciting at the time. And then just a few years ago, there was a major breakthrough, a very surprising breakthrough, where at this point, it wasn't even clear whether 3 should be the right base for this exponent. And that was a big open problem. And then there was a big breakthrough where the following bound was proved, that it was exponentially less than the previous bound. Okay? So this is the one I want to talk about in the first part of today's lecture. And so this development came first, the history is a bit interesting. So Crude, Lev, and Pak uploaded a paper to the archive May 5th of 2016, where they showed not exactly this theorem, but in a slightly different setting in this group, so in Z mod 4 instead of Z mod 3. And this was already quite exciting, getting exponential improvement in this setting. But it wasn't exactly obvious how to use their method to get F3. But that was done about a week later. So Ellenberg and Heischwitz, so they managed to improve use this technique, modify the Crude-Lev-Pak technique to the f3 to the n setting, which is the one that we've been interested in. So there's a small difference between these two, namely this group has elements of order 2, which makes things a bit easier to deal with. So this is the Crude-Lev-Pak method, so as is often called in literature, and we'll see that it's a very ingenious use of the so-called linear algebraic method in combinatorics, in this case the polynomial method. And it works specifically in the finite field vector space setting. So what we're talking about in this part of the lecture does not translate whatsoever. At least nobody knows how to translate this technique to the integer setting. Okay, so how does it work? The presentation I'm going to give follows not the original paper, which is quite nice to read, by the way. It's only about 4 pages long. It's a pleasant to read. But there's a slightly even nicer formulation on Terry Tao's blog, and that's the one that I'm presenting. So the idea is that if you have a subset of f3 to the n that is 3AP free, and such a set also has a name cap set, which is also used in literature in this specific setting where you have no 3 points on the line. Right, in this case, then we have the following identity. Okay, so here delta is the Dirac delta. Let me write that down in a second. So the delta of A is the Dirac delta is either 1 if x equals to A and 0 if x does not equal to A. So this is simply rewriting the fact that x, y, z form a 3AP if and only if their sum is equal to 0. And because you're 3AP free, the only 3APs are the trivial ones recorded on the right-hand side. Okay, so this is simply a recording of the statement that A is 3AP free. And the idea now is that you have this expression up there, and I want to show that if A is very, very large, then I could get a contradiction by considering some notion of rank. Right, so we will show that the left-hand side is, in some sense, low rank. Well, I haven't told you what rank means yet, but the left-hand side is somewhat low rank, and the right-hand side is a high rank object. All right, so what does rank mean? So recall from linear algebra, so the classical notion of rank corresponds to two-variable functions. So you should think of F as a matrix over an arbitrary field F. So such a function or a corresponding matrix is called rank 1 if it is non-zero, and it can be written in the following form. F of xy is f of x, g of y for some functions that are one variable each. Right, so in matrix language, so this is a column vector times a row vector. So that's the meaning of rank 1. And to say that something is of high rank, well, of a specific rank, rather the rank of f is defined to be the minimum number of rank 1 functions needed to write f as a sum or a linear combination So this is rank 1, and if you add up R rank 1 functions, then you get something that's at most rank R. Okay, so that's the basic definition of rank from linear algebra. For three-variable functions, you can come up with other notions of rank. Right, so what about three-variable functions? Right, so how do we define the rank of such a function? So you might have seen such objects as generalizations of matrices called tensors. And tensors have already a natural notion of rank, and this is called tensor rank. Just like how here f is, we say rank 1 if it's decomposable like that. We say f has tensor rank 1 if this three-variable function is decomposable as a product of one-variable functions. So the tensor rank, it turns out, okay, so this is an important notion, which is actually quite mysterious. There's a lot of important problems that boil down to us not really understanding what tensor rank, how it behaves. Right? And it turns out this is not the right notion to use for our problem. Right? So we're going to use a different notion of rank. Here, rank 1 is decomposing this three-variable function into a product of three one-variable functions. But instead, I can define a different notion. We say that f has slice rank 1. Okay, so this is a definition that's sort of introduced in the context of this problem, although it's also quite a natural definition. If it has one of the following forms. Right? So I can write it as a product of a one-variable function and a two-variable function. Okay, so one variable and the remaining two variables. But this definition should also be symmetric in the variables, so the other combinations are okay as well. Okay, so this is the definition of a rank 1 function, a slice rank 1, and also if non-zero. Right, so if it's non-zero and can be written in one of these forms. And just like earlier, we define the slice rank of f to be the minimum number of slice rank 1 functions. Right? Same as before, that you need to write f as a sum. So I can decompose this f into a sum of slice rank 1 functions. What's the most efficient way to do so? All right, so that's the definition of slice rank. And you see, you can come up with this definition for any number of variables, right? Where slice rank 1 means decomposing into two functions, where one function takes one variable and the other function takes all the remaining variables. And then for two variables, slice rank and rank correspond to the same notion. Okay, any questions so far? All right, so let's look at the function on the right. Okay, so think of it as a matrix, a tensor. So what is it? Well, it's kind of like a diagonal matrix. So that's what it is. It's a diagonal matrix. So what is the rank of a diagonal matrix? Okay, in this case, a diagonal function. Well, you know from linear algebra that if you have a matrix, then the rank of a diagonal matrix is the number of non-zero entries. So something similar is true for slice rank, although it's less obvious. It will require a proof. So if I have this three-variable function defined by the following formula, so in other words, it's a diagonal function where the entries on the diagonals are the CAs. Okay, so what is the rank of this function? So the slice rank of f, right? In the matrix case, it will be the number of non-zero entries, and it's exactly the same here. Right? So the number of non-zero diagonal entries. That turns out to be the slice rank. Okay, well, let's see a proof. So we go back to the definition of slice rank, and we see that one of the directions is easy. Okay, so I have this less than or equal to, greater than or equal to. Okay, so which one is easy? Okay, so you see, the right-hand side is a sum of R of A. Well, this many rank 1 functions. So this direction is, okay, so this direction is clear. Right, just looking at the definition, right, I can write f explicitly as that many rank 1, slice rank 1 functions. Okay, so the tricky part is greater than or equal to. And for the greater than or equal to, let's assume that all the diagonal entries are non-zero. Okay. So why can we do this? If it's not non-zero, I claim that we can remove this element from A. If the CA is not 0, then I remove A from the set. And doing so cannot increase the rank. Now, a priori, the rank might go down if you get rid of an entry, right? Because if you add an entry, even though the function doesn't change on the original set, if you increase your set, maybe you have more space, maybe you have more flexibility to work with. Okay. But certainly if you remove an element, right, so the rank cannot go up. Okay, now, so suppose the slice rank of f is strictly less than the size of A, so all these CAs are non-zero. So suppose for contradiction that there's some different way to write function f that uses fewer terms. Okay, so what would such a sum look like? So I would be able to write this function f in a different way. then now I look at these the other types of functions using a different combination of the variables. Okay, so suppose there were a different way to write this function f that uses fewer terms. Okay, so I assume it uses exactly the size of a minus 1 terms. I can always put in 0 functions if you like. Okay, so now I claim that there exists a function h on the set A whose support, so the support is a number of entries that give non-zero values. The support of f is bigger than m, such that the following sum is 0. For all so I claim that, okay, so we can find a function h such that, think of it as in the kernel of some of these f's. All right, so this is a linear algebraic statement. Okay, yes?
What is h sub sine of a minus 1?
Sorry, it's just h. It's a single function h such that this equation is true for all x's.
Is that not just h of x times the sum of all of that?
You are right. So, okay, so what do I want to say here? So we want to find a function h such that the support of h is at least m So, right, so what do we want to say? I want to say that yeah, so you're right. So this is not what I want to say. And instead, it's something okay, so let's see. So here we have some number of functions. So here we have some number of functions, and for each a, I have for each. Let's see. I'm sorry? No, so I do want to show, no, there's no inductions because I mean 3 variables and I want to get rid of, so the point is, okay, so let's see where we'll go eventually. And then we'll figure out what happened up there. So we want to consider So I would like to eventually consider the following sum. Okay, so I want to consider the sum, which comes from, okay, so you look at, wait, no, that's not the sum I want to consider. So let's look at this f of x, y, z. Okay, so f being that sum. So no. Okay, so take that f up there, and let me consider basically taking the inner product of this function viewed as a function in z. Okay, so consider this inner product. And if I think, okay, so what I want to say is not this. Okay, so what I want to say is, if I look at the inner product of h with the, okay, so take one of these f's. Okay, so take one of these f's and look at the bilinear form relating h and f. Okay, so I want to show that this sum vanishes for all I between n plus 1 and the size of a minus 1. Okay, so this rho, I want it to vanish when being taken bilinear form with h. Okay, so that makes sense now. Right. Okay, good. All right, so the fact that such a non-zero h exists simply is a matter of counting parameters. It's a linear algebraic statement. You have some number of freedoms, you have some number of constraints, right? And so the set of such h, okay, satisfying all of these constraints. So there are this many constraints. Well, each one of them could cut you down to one dimension less, but the set of such h is a linear subspace of dimension bigger than m, because I have a dimensions and I have these many constraints. Right? So the set of such h is, there are lots of possibilities. And furthermore, it is also true that, and this is a linear algebraic statement, that every subspace of dimension m plus 1 has a vector whose support has size at least m plus 1. Okay, I'll leave this as a linear algebraic exercise. It's not entirely obvious, but it is true. When you put these two things together, you find that there is some vector. So I think of the coordinates of the vectors as indexed by the set A. There is some vector whose support is large enough. Okay. Now, so we proved the claim. Let's go back to this lemma about this diagonal function having high rank. Take h from the claim. Okay, so let's take h from the claim. Then let's consider this sum over here. On one hand, what the sum is you can do the sum on the right-hand side. We see that it's like multiplying a diagonal matrix by a vector, So what you get following the formula on the right-hand side is the following. Okay, let me rewrite this part. Sum over A of C sub A, H of A, delta sub A of X, delta sub A of Y. Okay, just looking at the formula from the right-hand side. On the other hand, if you had a decomposition up there, doing this sum and noting the claim, we see that the third row is gone. So what you would have is a sum over these z's of, so let me write it like this. So you would have a sum that is of the form f1 of x and g tilde 1 of y, where g tilde is basically the inner product of g1 as a function of z with h. So fl of x, gl of y. And then also functions like that. Okay, so there exist some functions g which come from g tilde which come from the g's up there, such that this is true. Right. Okay, but now we're in the world of two variable functions. Okay. So left and right hand side are two variable functions, and for two variable functions, you understand what is the rank of a diagonal function. Okay. So the left hand side has more than m diagonal entries. Right? Because h has support, so the number of diagonal entries is just the support of h. Whereas the right-hand side has rank, so now linear algebraic matrix rank at most m. And that's a contradiction. Yep.
So we can show a similar statement for n variable functions, right?
Great. So we can show a similar statement for arbitrary number of variables by generalizing this proof and using induction on the number of variables. Okay. But we only need 3 variables for now. Okay. Any questions? So just to recap, what we proved is the generalization of the statement that a diagonal matrix has rank equal to the number of non-zero diagonal entries. But the same fact is true for these 3 variable functions with respect to slice rank. Okay, so this is sort of intuitively obvious, but the execution is slightly tricky. Okay. All right. So now we have this statement here. Let's proceed to analyze this function, which comes from, so this relationship here coming from a set A that is 3AP free. All right. So suppose now I'm in, okay, so everything so far works generally with any A, but now let me think about specifically functions on the finite field vector space f3 to the n. Okay, so it's a function taking value f3. And this function is defined to be the left-hand side of that equation over there. So the claim is that Okay, so the left-hand side claimed that this function has low rank. So we claim that the slice rank of this function is at most 3m, where m is the sum of, okay, so essentially this multinomial coefficient. Okay, so okay, we'll analyze this number in a second, but this number is supposed to be small. All right, so we want to show that this function here has small rank. So let's rewrite this function in a form explicitly as a sum of products. By expanding this function after writing it in a slightly different form. So in F3, in a three-variable, in characteristic, so in F3, you have this equation. Well, you can check that it's true for x equal to 0, 1, or 2. So take that and plug it in over here. So we find okay, so now x, y, z are in F3 to the n. So we find that applying this guy here coordinate-wise, so you have this product. Great. Now let's pretend we're expanding everything. Okay, so this is a polynomial in 3n variables. 3n variables, its degree is 2n. Okay, so if we expand, we get a bunch of monomials. And the monomials, they all have the following form. Okay, so the x's, whose exponents I call I, the y's, whose exponents I call j, and the z's, whose exponents I call k, where, so we get a sum of monomials like that, where all of these I, j's, and k's are either 0, 1, or 2. All right, so I get this big sum of monomials, and I want to show that it's possible to write this sum as a small number of functions that can be written as a product, where one of the factors only involves one of x, y, z. Okay. So what we can do is to group them. Okay, so group these monomials by the, okay, so for example, okay, so I'm going to group these monomials by using the following observation. So by pigeonhole, at least one of the exponents of x, or the exponents of y, or the exponents of z, at least one of these guys is at most 2n over 3. So I group these monomials by the one of x, y, z that has the smallest exponent. Right. So the contributions to the rank, or the slice rank, from monomials with the degree of x being at most 2n over 3. Well, I can write such contributions in the form like that, where this f of x is a monomial, and the g is a sum of whatever that could come up. This is a sum, but this is a monomial. So the number of such terms, okay, so the number of such terms is the number of monomials, well, corresponding to choices of i's that sum to 2n over 3, and individual i's coming from 0, 1, or 2. And that number is precisely m. So m counts the number of choices of 0, 1, 2's. There are n of them, and the sums of the i's is at most 2n over 3. Okay. So these are contributions coming from monomials where the degree of x is at most 2n over 3, and similarly with degree of y being 2n over 3, and also the degree of z being at most 2n over 3. Okay. So all the monomials can be grouped in one of these three groups, and I count the contribution to the slice rank. Okay, so question is, do we have a good idea as to how sharp this bound is? That's a really good question. I don't know. Yeah. Okay. Great. So that finishes the proof of this lemma. Okay. So now we have this lemma. I can compare. Okay, so we have these two lemmas. One of them tells me the rank of the right-hand side, which is A. So let's compare ranks. The slice rank. So the left-hand side, we know it is at most this quantity, and the right-hand side is equal to A. So we automatically find this bound. So now we want to know how big this number m is. Okay, so there's actually, this is a fairly standard problem to solve to estimate the growth of this function m. So let me show you how to do it. And this is basically the universal method. It's, notice that I can, if I look at this number here, where if, okay, so now x is some real number between 0 and 1, then I claim the following is true. And this is because if you expand the right-hand side and count your monomials, okay, so you can just keep track of which monomials occur, and there are m of them where you can lower bound by this quantity here. Okay, so this is kind of a related to things in probability theory on large deviations, called the Cramer theorem. But that's what you can do. So this is true for every value of x. So you pick one that gives you the best bound. So m is at most the nth of this quantity here. Okay? And you know, to show you any bound, I just have to plug in some value. So if I plug in, for example, x being 0.6, I already get a bound, which is the one that I claimed. Okay. And it turns out, you know, this step here is not lossy. As in, basically up to 1 plus little 1 in the exponent, this is the correct bound. Okay, and that follows from general results in large deviation theory. And that finishes the proof. Okay. Alternatively, you can also estimate m using Stirling's formula. Right? So, but this I think is cleaner. Great. Any questions? Yep.
Again, mx to the 2n over 3 is less frequent than 1 plus x greater than n.
Okay. So why is this step true? So if you expand the right-hand side, you see that the right-hand side is upper bounded by all these a, b, c, as in, same as over here, x to the b plus 2c. Right? And because how many terms, and also there's a binomial coefficient term. So basically, I'm doing the multinomial expansion, except I toss out everything which is not part of the index. Right? And because b plus 2c is at most 2n over 3, so I get m times x to the 2n over 3. It's okay? All right. Now, I want to convey a sense of mystique about this proof. Right? This is a really cool proof. And okay, so because your singing lecture maybe went by very quickly, but when this proof came out, people were very shocked. They didn't expect that this problem would be tackled, would be solved using a method that is so unexpected. And this is part of this power of the algebraic method in combinatorics, where we often end up with these short, surprising proofs that take a very long time to find, but they turn out to be very short. Right? So this is very short. This was basically a 4-page paper. But when they work beautifully. They work like magic. But it's hard to predict when they work. And also, these methods are somewhat fragile. Right? So unlike the Fourier analytic methods that we saw last time, where that method, it's very analytic. Works in one situation, you can play with it, massage it, make it work in a different situation. Here, we're using something very implicit, very special about these many variables. And if you try to tweak the problem just a little bit, the method seems to break down. Right? So in particular, it is open how to extend this method to other settings. It's not even clear what the results should be. Right? So it's open to extend it to, for example, 4 APs. Right? So we do not know if the maximum size of 4 AP free subset of f5 to the n is less than some constant of 4.99 to the n. Okay, so that's very much open. By the way, all of this 3AP stuff, right now I've only done it in F3, but it works for 3AP in any finite field. It also is open to extend it to corners. So you can define a notion of corners. So previously we saw corners in the integer grid, but replace integer by some other group. So you can define a notion of corners there. Okay, so not clear how to extend this method to corners. And also, is there some way to extend some ideas from this method to the integers? This completely fails. Right? So this method's not clear at all how you might have it work in a setting where you don't have this high dimensionality. I mean, the result will be different because in integers, we know that there's no power saving, but maybe you can get some other bounds. Okay, any questions? Okay, great. Let's take a break. So in the first part of today's lecture, I showed you a proof of Roth's theorem in F3 to the n that gave you a much better bound than what we did with Fourier. The second part, I want to show you another proof. Okay, so yet another proof of Roth in f3 to the n, and this time giving you a much worse bound. But of course, I do this for a reason. Okay, so we'll give you the new result. So we'll give you some more information about 3APs in f3 to the n. But the more important reason is that, in this course, I try to make some connections between graph theory on one hand and additive combinatorics on the other hand. And so far, we've seen some analogies in the proof of Semirades graph regularity lemma versus the Fourier analytic proof of Roth's theorem. There was this common theme of structure versus pseudo-randomness. But the actual execution of the proofs are somewhat different, because on one hand, in regularity lemma, you have energy increment. You have partitioning and energy increment. And on the other hand, with Roth, you have density increment. Right? You're not partitioning, you're zooming in. Take a set, find some structure, zoom in. Find some structure, zoom in. You get density increment. Okay, so it's similar, but differently executed. So today, this second half, I want to show you how to do a different proof of Roth's theorem that is much more closely related to the regularity proof. Right, so that has this energy increment element to it. And I show you this proof because it also gives you a stronger consequence. Right? And namely, we'll get that there is also not just 3APs, but 3APs with popular difference. So here's the result that we'll see today. So it's proved by Ben Green that for every epsilon, there exists some and not, such that every A being subset of f3 to the n with density alpha, there exists some non-zero y such that the number of 3APs with common difference y. Okay, so let's think about what's going on here. So if I just give you a set A and ask you how many 3APs are there, and compare it to what you get from random, right? Random meaning, well, if A were a random set of the same density. Right? So the question is, can the number of 3APs be less than the random count? Okay, and the answer is yes. So for example, you could have, in the integers, you can have a Barron type construction that has no 3APs. So certainly that has fewer 3APs than random. And you can do similar things here. But what Green's theorem says is that there exists some popular common difference. So this is a popular common difference such that the number of 3APs in A with this common difference is at least as much as what you should expect in a random setting, up to a minus epsilon. Okay, so this is a theorem. Okay, so let me say the intuition again. It says that given an arbitrary set A, provided the space dimension is large enough, there exists some popular common difference, where popular means that the number of 3APs with that common difference is at least roughly as many as random. In particular, this proves Roth's theorem, right? Because you have at least some 3APs. But it tells you more. It tells you there's some common difference that has lots of 3APs. Even though on average, if you just take an average, if you take a random y, this is false. Okay? Any questions about the statement? All right. So Green developed an arithmetic analog of Semiramis graph regularity lemma in order to prove this theorem. Okay, so starting with Semiramis graph regularity lemma, he found a way to import that technique into the arithmetic setting in f3 to the m. Okay, so I want to show you roughly how this is done. And just like in Samueli's graph regularity lemma, there were unavoidable bounds which are of tower type. The same thing is true in the arithmetic setting. So Green's proof shows that the theorem is true with n naught being something like tower in a tower of 2's. The height of the tower is polynomial in 1 over epsilon. Okay, so just like in regularity lemma for graphs. So this was recently improved in a paper by Fox and Pham just a couple years ago, where, and this is a proof that I will show you today, where you can take n naught to be slightly better, but still a tower. But tower of now height log in 1 over epsilon. Okay, so really, really big tower to just slightly less big tower. But more importantly, it turns out, and so they also showed that this is tight. You cannot do better. There exists constructions, there exist sets A for which this theorem is false if you replace the big O by less than some very small constant. So many applications of the regularity lemma, the first proof may be using regularity and it's difficult, it gives you a very poor bound, but subsequently there were other proofs, better proofs, that give you non-tower type bounds. But this is the first application that we've seen where it turns out the regularity lemma gives you the correct bound. Right? So it's really, you need a tower type bound. I mean, we know the regularity lemma itself needs tower type bounds, but it turns out this application also needs tower type bounds. That's quite interesting. Right? So here, the use of regularity is really necessary in this quantitative sense. Okay, so let's see the proof. So let me first prove a slightly technical lemma about bounded increments. Okay, so this corresponds to the statement that if you have energy increments, you cannot increase too many times. But in a slightly different form. Okay. So suppose you have numbers alpha and epsilon bigger than 0, and if you have this sequence of A's between 0 and 1, and such that A naught is at least alpha, then there exists some k at most log base 2 of 1 over epsilon, such that 2a sub k minus a sub k plus 1 is at least alpha cubed minus epsilon. Okay, so don't worry about this form. We'll see shortly why we want something like that. But the proof itself is very straightforward, right, because otherwise, so you start with a naught. Now then, if this is not true for k equals to 0, then a1 is at least 2 a naught minus epsilon cubed plus epsilon. Okay, so a naught is at least alpha cubed. Right, so if otherwise you have some lower bound on alpha 1, so which is at least alpha cubed plus epsilon. And likewise, you have some lower bound on alpha 2. You have some lower bound on alpha 2. And this lower bound is plus 2 epsilon. Okay, so you keep iterating. You see the next thing is 4 epsilon, and so on. So if you get to more than this many iterations, you go more than 1. So alpha k is bigger than 1 if k is ceiling of log base 2 of 1 over epsilon. And that will be a contradiction to the hypothesis. Okay, so this is a small variation on this fact that you cannot increment too many times. Each time you go up by a bit. Whereas we save a little bit because the number of iterations is now logarithmic because you double in epsilon each time. All right. If I give you a function f on f3 to the n, and u is a subspace. Okay, so this notation means subspace. Let me write f sub u to be the function obtained by averaging f on each u coset. Okay, so you have some subspace, you partition your space into translates of that subspace, and you replace the value of f on each coset by its average on that coset. Okay, so this is similar to what we did with graph functions. You're stepping, so you're averaging on each block. Okay, so now let me prove something which is kind of like an arithmetic regularity lemma. Okay, and I mean this statement will be new to you, but it should look similar to some of the statements we've seen before in the course. Right. And the statement is that for every epsilon, there exists some m, which is a function of epsilon, and in fact, it will be bounded in terms of power of height and most order logarithmic in 1 over epsilon, such that for every function f on f3 to the n that are values bounded between 0 and 1, there exist subspaces w and u where the codimension of w is at most m. So you should think of this as the coarse partition and the fine partition in the partition regularity lemma. Right? And the codimension corresponds to the number of pieces. Right? So 3 raised to codimension is the number of cosets. So you have bounded many parts, and I have 2 partitions. And what I would like is that the number, okay, so if I want f to be sort of pseudo-random after doing this partitioning, so to speak, and this corresponds to the statement that if I look at f minus fw, then the maximum Fourier coefficient is quite small, where quite small means at most epsilon over the size of u complement, so size of u perp. And also, there's this other condition which tells you that the L3 norms between f sub u and f sub w are related in this way. So we haven't seen this before. In fact, specifically this inequality is very ad hoc to the application of popular difference in 3APs. But we have seen something similar where this relationship is replaced by something that accounts for the difference between L2 norms. So if you go back to your notes, when we discussed regularity lemma in a more analytic fashion, we have that. And you should think of this, when we discussed strong regularity lemma, this definition here is roughly corresponds to a definition that in the fine partition versus the coarse partition, the edge densities are roughly similar. That when you do the further partitioning, you're not changing densities up by very much. Okay, so that's the arithmetic regularity lemma. And once you have the statement, I think the hardest part is writing down the statement. Once you have the statement, and the proof itself is kind of this follow your nose approach, where you first define the sequence of epsilons. Epsilon naught is 1, and epsilon sub k plus 1. Okay, so don't worry about this for now. You will see in a second why these numbers are chosen. Let me write R sub k to be the set of R's, so there will be characters, such that the Fourier coefficient at R is at least epsilon sub k. Okay, so the R's are supposed to identify how we're going to do the partitioning. Now, the size of this R is bounded. So we claim that the size of R is at most 1 over epsilon sub k squared. And that's because there's this Parseval identity which tells you that the L2 sum of the Fourier coefficients is equal to the L2 of the function, which is at most 1. So the number of Fourier coefficients that exceed a certain quantity cannot be too many. Okay. So let U now be the subspace defined by taking the orthogonal complement of these R's. And let's note that if we take alpha sub k to be the L3 norm cube of the function derived from averaging f along the u's, and then looking at the third moment of these densities. Right, so these alphas, we can apply the increment lemma initially to deduce that there exists, okay, so in particular this number here is at least alpha cubed by convexity. So by the previous lemma, there exists some k no more than on the order of 1 over a log 1 over epsilon, such that 2 alpha sub k minus alpha sub k plus 1 is at least the density of f cubed minus epsilon. Okay, so this alpha is supposed to be the density of f. All right, so we find this k, and we have this bound over here from satisfying that inequality. So this is the density increment argument, the energy increment argument. So we're doing the energy increment argument, basically the same argument as the one that we did when we discussed graph regularity lemma, but now presented in a slightly different form, in a different order of logic, but it's the same argument. And what we would like to show is that you also have this pseudo-randomness condition about having small Fourier coefficients. So what's happening here with the Fourier coefficients? Now, how is the Fourier coefficient of an averaged f related to the original f? So that's something we want to understand up there. And that's something that's not hard to analyze, because if you have a function u or w, so either one, then the Fourier coefficients of this averaged version is very much related to the original function. It turns out that if you take an R which is in the orthogonal complement, then the Fourier coefficient doesn't change. And if you are not in the orthogonal complement, then the Fourier coefficient gets zeroed out. Okay, so that's that's something that's not too hard to check, and I urge you to think about it. So with that in mind, let's go back to verifying this over here. So what we have now is that so this quantity, which measures the largest Fourier coefficient, the difference between f and u sub k plus 1, is at most. And what u sub k plus 1 is doing is we're looking at possible large Fourier coefficients, and we are getting rid of them. Right, so we're zeroing out these large Fourier coefficients so that the remaining Fourier coefficients are all quite small. But we chose our R so that this big R, so that if your little r is not in the big R, then the Fourier coefficient must be small. That's how we chose the big R. So we have this bound over here. And by the definition of the epsilon, we have that bound. So we're combining with this estimate, upper bound estimate on the size of R sub k. Okay, so point being, we have that. So now take w to be u sub k plus 1 and u to be u sub k, and then we have everything that we want. Question? Yeah.
Why is the codimension of W small?
Okay, questions. Why is the codimension of W small? Right, so what is the codimension of W? Okay, so we want to know that the codimension of W is bounded. Right. So the codimension of W is, well, I mean, the codimension of any of these u sub k's is at most 3 raised to the number of r's that produce it. Right? And the size of R is bounded. So if we pick M to that, so that it uniformly bounds the size of R, then we have a bound on the codimension. Okay, so that's important. Right? So we need to know that the codimension is small. Otherwise, if you don't have the bound on the codimension, you can just take the zero subspace. And trivially, everything is true. We have a regularity lemma, and what comes with the regularity lemma is a counting lemma. Okay, so let me write down the counting lemma, and I'll skip the proof. So the counting lemma tells you that if you have f and g, both functions on f3 to the n, and u is a subspace of f, then, okay, so let me define, so the quantity that I'm interested in is, so I'm interested in understanding 3 APs where the common difference is in a particular subspace. Okay, so we claim that the 3AP count of F with common difference restricted to the subspace U. So it's similar between F and G if F and G are close to each other in Fourier. Well, not quite, because, okay, so something like this we saw earlier in the proof of Roth's theorem. If we don't restrict the common difference, turns out if you restrict the common difference, you lose a little bit. Okay, so you lose a factor which is basically the size of the complement of U. Okay, so I won't prove that. But now let me go on to the punchline. Okay, So if we start with, again, f function in your space, taking values between 0 and 1, and I have subspaces u and w, so I claim that if I look at f averaged through w, and I consider 3 AP counts with common difference restricted to u, then this quantity here is lower bounded by this difference between L3 norms. Okay, so I claim this is true. So this is just some inequality, right? This is some inequality, and so of all the things that I did back in high school doing math competitions, I think the one skill which I think I find most helpful now is being able to do inequalities. Okay? And I thought I would never see these 3 variable inequalities again, but when I saw this one, so Fox and Pham, when they first showed me a somewhat different proof of an approach that didn't go through this specific inequality, I told them, hey, there's this thing I remember from high school. It's called Schur's inequality. And I thought I would never see it again after high school, but apparently it's still useful. So what Schur's inequality says, so this is one of those 3 variable inequalities that you would know if you did math Olympiads, right? That you have, okay, so it's an inequality between non-negative, actually it's true for real numbers as well, but let's say it's non-negative real numbers. Okay, so that's Schur's inequality. So if you look at the left-hand side, the left-hand side it can be written as a sum in the following way. It can be written in the following way. So it's expectation over x, y, z that are 3 APs in the same U coset. Okay, so I'm counting 3 APs with common difference restricted to U. So common 3 APs in the same U coset. And I am looking at the product of f sub w evaluated on this 3 AP. So what I would like to do now is apply Schur's inequality to A, B, and C being these 3 numbers. So the point is you have this ABC on the left, and then everything on the right involves only a subset of ABC. And they simplify. So if I do this, then I lower bound this quantity by twice the expectation of x and y in same coset, same U coset of f sub w of x squared and f sub w of y. Maybe I've took 2 other things, but they're all symmetric with respect to each other. And minus the term that corresponds to this sum of cubes. Like that. Okay, so this is a consequence of Schur's inequality applied with ABC like this. But now you see over here, I can analyze this expression even further, because if I let y vary within the same U coset, then over here it averages out to U cosets. Right? So U is bigger than W. So what we have is, so what we have over here is that it is at least twice of f of f, f of u, so fw squared fu minus expectation of fw squared, fw cubed. And I can use convexity on f sub w to get that. Okay, which is what we're looking for. So the last step is convexity. Okay, so I'm running through a little bit quick here because we're running out of time, but all of these steps are fairly simple. Once you observe, the first thing you can do is search inequality. And we're almost there. Right? So we're almost done. We're almost done. So from that lemma up there, I claim now that for every epsilon, there exists some m, which is power log in 1 over epsilon, such that if f is a function of f3 to the n, taking values between 0 and 1, then there exists a subspace U of codimension at most m, such that the 3AP count, 3AP density with common difference restricted to U is at least the random bound minus epsilon. Okay. Why is this true? Well, we put everything together. We can choose U and W as in regularity lemma. And by counting lemma, we have that the 3AP density of F, so it is at least, okay, so we're using counting lemma over here, it is at least the 3AP density of F sub W, view minus a small error, which we can control. Okay, so this step is counting. And now we apply the inequality up there. And finally, we chose our U and W in the regularity lemma so that this difference here is controlled. Right? So it is controlled by the random bound minus epsilon. And that's it. Okay? So you change epsilon to 4 epsilon, but we can change it back, and that's it. So we have the statement that you have this subspace of bounded codimension where you have this popular difference result. It doesn't quite guarantee you a single common difference because, well, you don't really want it to be the case where U is just a single point, right? Because I want a non-zero common difference. But if U is large enough, right, if N is large enough, I've bounded codimension so that the size of U is large enough. So then there exists some non-zero common difference. You pick some non-zero element of U. On average, it should work out just fine. Okay, so I'll leave that detail to you. One more thing I want to mention is that all of this machinery involving regularity and Fourier, as with things we've done before, carries over to other settings, general abelian groups, and also the integers. And you might ask, well, we have this for 3 APs. What about longer arithmetic progressions? In the integers, it turns out it is also true that Green statement in the integers if you replace 3 AP by 4 AP. That's a theorem of Green and Tao involving higher order quadratic analysis, quadratic Fourier analysis. However, and rather surprisingly, so 4 AP is okay, but 5 AP and longer, it is false. the corresponding statement about popular differences for 5AP in the integers is false. They are counterexamples. So it's really a statement about 3APs and 4APs. And there's some magic cancellations that happen in 4APs that make it true. Okay, great. So that's all for today.